Alright, so here we are, guys. It's our first one of these. It's going to be strange for me. I apologize for the poor quality audio. The microphone that I ordered was delayed, so hopefully we'll get that soon. I also apologize for my writing. This pen is not the easiest to use, so it's going to be a little bit rough here, but we'll do our best. Alright, so this is our first section in Chapter 6. And the main thing in this section is this concept of net change. Really, this section is not anything new. The net change theorem, the main theorem that we're going to talk about in this section, really is just the fundamental theorem of calculus with different words to go along with it. So we're going to start off studying this concept of net change by looking at some examples that we're used to, which would be displacement, problems involving position functions and velocity, and then also we'll go from velocity and acceleration as well. Then at the end we will generalize the concept into what we call the net change theorem. So let's go ahead and jump in. So as you recall, we've seen these examples before. So as we have a train moving along a track at a steady rate of 75 miles per hour, so constant velocity, and it's traveling from 7 a.m. to 9 a.m., so a total of 2 hours. If we want to know the total distance traveled by the train, well, we know distance is rate multiplied by time. So distance will be the rate, which is the velocity, 75 miles per hour, multiplied by the amount of time. We could represent that amount of time by delta V, a change, that's delta T, a change in time rather than delta V, and which is obviously 2 hours. So finding the distance traveled is just multiplying. In other words, we're finding the area of this rectangle. So same thing we've been doing. We'll skip the quick check for now. We can generalize this concept, and so the idea is if you have a velocity time curve, then finding the area under the velocity time curve is equivalent to finding displacement. So the important thing here is really this equation, and this really is the net change theorem. It says if we integrate a rate of change, we integrate the rate of change in the position that is equal to the net change in position. So this here is a net change. Obviously, we can approximate this with a Riemann sum if we needed to. So if we actually wrote the integral out using the limit notation, this actually kind of illustrates where differential notation comes from. So the idea is displacement is just a bunch of small displacements added up. And then eventually we make those small displacements so infinitesimal that we have infinitely many of them. And that's where we get the integral from. But this notation is really what this turns into. When we take the limit as n goes to infinity, these small displacements can be written in differential form. And if we take a closer look at this expression, we know that v of t is really the derivative of position. So this differential form could actually be written as s prime of t times dt. Right? This is the same as this thing here. And if we recall just the definition of how differentials work, this is actually the same as writing ds. So this entire integral is actually the same as this integral after we make a substitution, technically a u substitution. So this kind of illustrates a little bit why we use this differential form to begin with. I don't want to dwell on this because we're not going to really use this much, but I thought this would as a nice little way of representing where the differentials kind of come from. Okay, so this just kind of lists some of our important properties here. We're going to let s of t be the position function traveling along a straight line, and t is going to be the variable for time. Velocity, we already know that velocity is the derivative of position. And then based off of what we just kind of explained, displacement, which is a net change in position, can be given by this formula here. And this really is the fundamental theorem of calculus because v of t is really s prime of t. Right, so when we integrate a derivative, they cancel, and we just get this. All right, some of the problems are also going to ask us to do distance traveled. If we want distance traveled, then we simply need to integrate the absolute value of velocity, because we said that before when we defined this, that is actually what speed is. So geometrically, the way to think of it is, if you're trying to find displacement, you are finding net area under a curve. Right? The net change in position is going to be equivalent to the net area under the velocity time curve. So in this case, it would be this area minus the area here, since it's below the x-axis. If instead we want distance, then the idea is we need to take the absolute value of this curve. If you take the absolute value of it, the positive part stays where it is, doesn't change at all, but the negative part of the curve will flip over the x-axis. So then we would simply be finding the area of these two pieces and adding them together. Okay, so let's try an actual problem. So we've got a jogger. They run along a straight road with a velocity given by this function here, where t is going to be measured in hours. First part is to graph it over the time interval 0 to 3. So we're going to try to graph this by hand. It'll be a good review of things that we did actually back in college algebra. So in order to graph it, the first thing that I want to do is actually figure out when the velocity is 0. So if we set that function equal to 0, 2t squared minus 8t plus 6, set it equal to 0. First thing that I would do is factor out the 2. That gives us this. Just make it a little easier to factor. Alright, so this one factors easily. We can see it's going to be t minus 3 and t minus 1. Alright, so that gives us solutions of 3 and 1. So this is when velocity is 0. So if we come over here, we have velocity 0 at 1, velocity 0 at 3. We also know, if we're graphing this, the y-intercept is 6. Alright, so then we just need to do connect the dots. And this is where it's going to get ugly. I tried this earlier and I did not do very well. Alright, that's okay. Alright, so this gives us a rough sketch of the velocity. Now, once we have the velocity time curve, we can tell when it's moving in a positive or forward direction and when it's going in the runner is going in a reverse direction. Okay, so let's do forward first. So forward meaning in a positive direction. So whenever velocity is positive, we're moving forward. So it's going to be from 0 to 1. Now for this one, we do get to include the 0 because at that specific time, the velocity is positive, so we are moving forward. But we do not include the 1 because velocity is 0 at that time. So closed on the left, open on the right. Alright, I'm going to say backward for negative direction. So that's going to be between between 1 and 3. And both of those would be open. So that's it. Over here, the velocity is positive, but we're not going to include that because it's not in the interval that we're discussing for this one. Okay, so that's all we needed for part A. So for part B, it says find the displacement. So we're supposed to do those 3 different displacements. Alright, so each displacement can be done with a definite integral. So the first one, the displacement formula is this, but I don't have a position formula given. All we had was velocity. But we know this is going to be equal to the integral from 0 to 1 of the velocity function, which was 2t squared minus 8t plus 6 dt. Alright, you can easily do that integral. We're going to skip and go right to the answer for that, so I think that comes out to 8/3. Right, and units on this one, I guess, are miles. So that was the displacement over the interval here. Notice that that displacement is also the distance traveled since velocity is positive on that entire interval. All right, next displacement, s of 3 minus s of 1. Again, just do the definite integral from 1 to 3. And I'm just going to write v of t instead of writing the function out. And for that one, that is the area here, which comes out as a negative number, and it comes out as negative 8/3. Now, without even doing the math, the last one, we want the displacement on the interval from 0 to 3. And we can see the area above was equal to the area below, so we know that that is going to come out to 0. So s of 3 minus s of 0, again, is a definite integral. And it comes out to 0. Which makes sense. You know, the runner went forward for 8/3 mile, and then they came back the same distance. So they returned to their starting place, which is why the displacement is 0. One interesting thing to note, though, it took them 1 hour to go 8/3 mile, and then on the return trip, it took 2 hours. So they're slowing down. They're tired on the way back. All right, let's try another example. Oh, actually, no, there's part C here. Okay, so it said distance traveled. So to do distance traveled, what would happen is we would need to do, let's actually just write it out first. So distance is again an integral, but it'd be the integral from 0 to 3 of the absolute value of 2t squared minus 8t plus 6 dt. Now, if you needed to do this by hand and actually show all the work, we don't know how to integrate the absolute value. So what you would do is you would figure out, when is this thing 0? Well, lucky for us, we already did that. We know it's 0 here. So then you could break this up into two separate integrals. We could integrate from 0 to 1. This we know is going to come out positive because velocity is positive. But on the second piece, the velocity is negative, so we're actually going to subtract that area, because in the integral, the area would come out negative anyway. Right, so this would be the area corresponding to that region. This is the area corresponding to that region, but it comes out negative. This negative cancels it. So we already found these, though. This was 8/3 minus that one was negative 8/3. So as we said, the negatives cancel, so we get 16/3 miles. So this is the general process for finding distance. If you have to do it by hand, you set velocity equal to 0, and that tells you where to break up your integral. You integrate each piece. If it's already above the x-axis, then you just integrate it. If it's below, you put a minus in front of it. All right, let's move on. Okay, so our goal right now then is we want to come up with a formula for the position of an object. Suppose they gave you velocity, like they did in the previous problems, and we want to generate a formula, the future value of position. So if we start, we can integrate velocity over any interval we want. So I'm going to integrate it over 0 to t. But remember, velocity is the same as the derivative of position. And the fundamental theorem of calculus says that these two things are going to cancel, and I just evaluate the position at t and evaluate it at 0. So this whole thing here is just the second form of the fundamental theorem of calculus. But this gives us a formula we can solve for s of t. All I need to do is add this over here, and it gives you this formula. And this formula will work in general. So if you need to write down a formula for position, it's just the initial position plus this accumulation function. Now it turns out that this actually is true at any point, meaning I don't have to have the initial position. I can have any number there I want, and it's still true. So even if it wasn't the very first position, if you know any position, can just put whatever time that is in both of those places, and this formula works in those cases as well. Okay, so this is just stating the exact same thing. So let's use it. All right, in this problem, we have a block that hangs at a rest from a massless spring at the origin. That's telling us the starting position is 0. And at t equals 0, it's pulled down to... sorry, it does not actually start at the origin. I said that wrong. They're saying that the origin is the 0 position, but the starting position is actually 1/4. And we're counting the origin as 0, so if we pull it down, we're going to say the starting position is a -1/4. It is then released. So the velocity can be given by this formula. Now the reason this formula works is because we are in happy science land, massless spring. So this function oscillates infinitely many times, which means that our spring is never actually going to slow down. It's just going to keep bouncing, 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 which is not how it works in the real world, but that's because you don't have massless springs. Okay, we are going to define the upward direction to be the positive direction, and then going down is the negative direction. Okay, so goal is to get a formula for position. So to do that, there are two different methods that can be used. Where's the question? I guess I skipped the question. So part A did say to get a formula for position. So I'm actually going to show you what I think is the better way first, and then I'll go through the formula that we just had up there before. So the idea is this is really a differential equation. What it really says is s prime of t is equal to 1/4 sine of t. The derivative of position is this. So we just need to solve this differential equation with the initial condition that s of 0 equals -1/4. And I think treating it as a differential equation actually makes the process easier. So what I'm saying is that s of t in general is always the antiderivative of v of t dt plus some constant. We will figure the constant out by using the initial condition. So let's just plug everything in. So notice here I'm doing an indefinite integral, not a definite integral. So we are integrating 1/4 sine of t dt. Keep the plus c out here. Antiderivative of this is going to be -1/4 cosine of t plus our constant c. All right, so now we use our initial condition, s of 0, plug 0 into this, -1/4 cosine of 0 plus c. But we know this is -1/4 on the left, and then we can start evaluating this. So -1/4 cosine of 0 is 1, so that's -1/4. A little messy. If I add this over, then we get 0 is equal to c, which is nice for us. So the constant came out to 0. All right, so conclusion is our position function is just -1/4 cosine of t. And that's that. This method will always work as long as you have an initial condition. I think it's the fastest way, but let's look at the other way. So the other way is to use the formula that we had before. That formula said s of t is equal to s of 0 plus an accumulation function from 0 up to t of v of x dx. We have to plug everything into this. So we know s of 0 is -1/4. Integrating from 0 to t, and we have 1/4 sine of x dx. So notice the difference here is that we're doing a definite integral where we had an indefinite integral before. But what the benefit of this is we won't have to do the extra step of solving for c. That will happen naturally when we evaluate the definite integral. So we have -1/4 plus antiderivative again is -1/4 cosine of x dx. Oops, sorry, I don't need that. We are evaluating that at 0 and t. All right, so here we got to be careful with our signs. I'm going to keep the negative 1/4 on the outside. Plug in t first. Okay. All right, let's scroll this down. Okay, so cosine of 0 is 1. And when we distribute, this is going to become plus 1/4, which will end up canceling this. So you can see we do get the same thing. So, is it faster, not faster? I don't know. I will probably keep defaulting to the first method, but if you like this method, it works. Okay, so let's go to the next part. So now it says to graph the position function. So remember we've said position was negative 1/4 cosine of t. So this gives us an opportunity to remember some pre-calc things here. The negative 1/4, really the 1/4, becomes our amplitude. Negative tells us we are flipped over. So the cosine is going to start down here because it normally starts at the top. And then it's going to oscillate. Period has not changed, so a full period is 2 pi. I've broken that interval down into 4 pieces, so it's going to just keep oscillating back and forth. And I think it only said, oh, it does say to 3 pi. All right, so here we go again. This is going to be not pretty, but we'll try our best. Pad I'm using is for artists. I have no idea, oh, that's horrible, how an artist is supposed to make anything out of this. Okay, so that gives us the graph of the position function. So now let's answer these. It says, when is it moving through the origin for the first time? So keep in mind, this is position now. This is not velocity. So moving through the origin means position of 0. So that is going to be right here. So for that first question, it is just when t equals pi over 2. All right, I thought there was a second part to this. I guess that's it. Okay, these are in seconds as well. Now, I did have a part D. Oh, there it is. I forgot to shrink it down. All right, give me a second here. All right, so then the next one says, when does it reach the highest point for the first time? So this is position again. So highest point does mean the highest y value. So the first time it hits the highest point would be at t equals pi. And what is the position at that time? At that time, s is equal to 0.25. 0.25. And I think those were meters. So at pi seconds, it hit the highest point that it reaches, which is 0.25 meters above the origin. All right, then it says, when does it return to its lowest point? The lowest point is 0.25. It's saying return, so this is the second time it gets there, so that's going to be t equals 2 pi seconds. All right, so that's all it's asking for. I think that's pretty easy, actually. Pretty self-explanatory, hopefully. Okay, so let's go ahead and do this quick check. So it says, without doing further calculations, what are the displacement and the distance traveled? All right, so let's do displacement first. I know it said don't do additional computations, but notationally, the displacement over 0 to 2 pi would be s of 2 pi minus s of 0. Ending position minus starting position. So here's ending position minus starting position. Well, they're the same thing. So obviously, it's 0. Over that interval, the change, net change in position is 0, because it ended up back where it started. Okay, so then distance, well, distance is going to be just adding up these different distances. So like, for example, here, it traveled 1/4 of a meter to get to this point. It traveled another 1/4 of a meter to get here, another 1/4 of a meter here, and another 1/4 of a meter here. So that was 1, 2, 3, 4, 1/4 of a meters. 4 times 1/4 of a meter is 1. All right, let's try another application. So it's a little messier. It says, suppose a skydiver leaps from a hovering helicopter and falls in a straight line. He reaches terminal velocity of 80 meters per second at approximately, or I guess at the starting time, just to make it convenient for us. And he falls for 19 seconds. At that time, he decides, okay, we better open the parachute, so he pulls the cord, and that starts to slow him down. His velocity, let's say, decreases linearly, as a linear function, to 6 meters per second over a period of 2 seconds. And then it remains constant until he reaches the ground at t equal 40 seconds. This would be the 6 meters per second is the new terminal velocity with the parachute being open. So that whole situation could be modeled with this piecewise function, which we could have actually written that ourselves. Would have made the problem maybe more interesting. So this was the initial terminal velocity over the first 19 seconds. We pulled the cord to the parachute at 19 seconds and slowed down over the next 2 seconds to 6 meters per second and stayed at that until we hit the ground. Okay, so the question is to determine the altitude from which the skydiver jumped. Well, let's think about that. So if we're determining the altitude, the skydiver only went down. So the distance that he traveled is the same as displacement in this case. So what we're really doing is s of 16 minus s of 0. The starting or ending position minus the starting position, the net change. So to do that, that's going to be the integral from 0 to 16 of v of t dt. Well, how are we going to integrate a piecewise function? Well, the easy way to do it is just break it up into separate integrals. So this is integral from 0 to 19, be our first one. Oh, sorry, that is a mistake there. Yes, I don't know where I got 16 from. The time interval was 0 to 40. Let's fix that. All right, so first one is 0 to 19, and it is just a constant in there of 80 dt. That's the velocity during that time. All right, then do the second one. So integral from 19 to 21 of 783 minus 37 dt. Plus the final one, which is, oh, it looks like that's a typo. I should say 21. It's good to see some things never change. All right. So we get that. Okay, so then we do each integral. These are constant functions. So this really represents the area under a rectangle. This is the height of the rectangle. So the velocity would be the height, and the width would be 19. So the first one is just 80 times 19. Second one, you'd have to go through and integrate. So 783t minus 30. Oh, I forgot my t in there too. So it'll be 37t squared over 2. Evaluated at 21 and 19. And then again, another rectangle here. So that last rectangle would be 6 times 40 minus 21. Okay, so you do all that math, and this should come out to 1,720 meters. So total distance distance traveled over the 40 seconds that we were dropping. All right, let's see, was there a part 2 to that? No, there's not a part 2, but there is a picture here modeling what we actually did. So we did distance traveled, which again, as I said, distance traveled is the same thing as displacement because velocity is always positive in this problem. Velocity is never negative, so we don't have to worry about these absolute values actually. So this is exactly what we did, integrating those 3 separate things, found the area on each of these pieces, 2 rectangles and a trapezoid in between them. Okay, I think this quick check's actually worthwhile doing. So this just tweaks the problem slightly. It says, suppose, unrealistically, that when we pulled the parachute, we immediately dropped to this velocity. So we hit terminal velocity of 80, and then at 20 seconds, they're going halfway through this interval here. They said that we pulled it at 20, and immediately we were down here. So it says sketch what the velocity curve would look like, and then figure out what the distance traveled would be in that case. So the way the curve would be different is this would just extend over to that point, and this would go over just a little bit further. So what you'd end up with, can't probably draw a straight line, is just 2 different rectangles. A rectangle here and a rectangle here. So in this case, distance would be the area of this first rectangle. The width of it is 20. The height of it is 80. That's this rectangle. And then for this one, it would be a distance again of 20 multiplied by a height of 6. And we see that this is 1600 plus 120. We get 1720. So it turns out to be the exact same thing. So this is just illustrating that if you do have something that is decreasing linearly, you can actually kind of ignore that part and just basically say that the instantaneous change occurred rather than worrying about the middle part. Okay, so we did the problems with velocity. Let's move on to acceleration. These basically work the exact same way. It's not really different. So if we're interested in finding a change in velocity, well, this is how we would write change in velocity, just the difference between 2 velocity values. But this could be thought of as the answer to an integration problem. Fundamental theorem of calculus says that this integral is actually this difference. But the derivative of velocity is actually acceleration. And this last part is just doing a change of variables again and showing that you are where the differential form actually comes from. But the main structure of it is exactly the same that we saw before, which says the net change in velocity is an integral of the rate of change in velocity. That is the net change theorem. Then, using the same reasoning as we did before, you could write down a future value formula for velocity. So this is the exact same thing we had for position, not different at all, just change the variables. The exact same thing. Okay, so let's look at an example with this. Alright, so in this example we have somebody doing something incredibly stupid. They're shooting an artillery piece directly vertically, so it will theoretically come back down on that gun. So it says an artillery shell is fired directly upward with an initial velocity of 300 meters per second from a point 30 meters above the ground. Assume that only the force of gravity acts on the shell, and it produces an acceleration of 9.8 meters per second squared, so meaning we're on Earth. We're going to find the velocity while the shell is still in the air. So we're just supposed to find the v of t formula. So one way to do this, we could say v of t is equal to v of 0 plus the integral from 0 to t of a of x dx. That's really bad. So that's the formula we had just a second ago. But we can also do the formula that I had before, where we said velocity is the antiderivative of acceleration plus some constant. So either one of these is going to work just fine. So let's use the second one. All right, we were given the acceleration is constant. The only acceleration is the force of gravity. The force of gravity is pulling us down, which means we're going to use, it's going to be a negative. Acceleration is always negative because it's pulling against the motion. So negative 9.8 dt plus c. All right, well, we're just integrating a constant, so the antiderivative of that is 9.8 t plus c. And now we need to find the value of the c. So this is where the initial condition comes in, and that was that v of 0 was given to be 300. All right, so if we do that, 300 equals negative 9.8 times 0 plus c. That's going to get wiped out, so we get c is 300. All right, this gives us our velocity function. V of t is just negative 9.8 t plus 300. You'll notice we did not actually use this at all. So why is it here? Well, the problem may go on and actually ask us to find the position. So we could go through this whole process. We could say that s of t is the antiderivative of negative 9.8 t plus 300 dt plus, again, some new constant. Do the antiderivative of this and use this initial condition to find the value of c. So we're not going to do that here, but if you were asked to find position, we could do that. Okay, so we now just want to kind of generalize all of this into a specific theorem. The problems that we've done, whether it's velocity or acceleration, they're all modeling basically the same exact relationship. So we're going to let q be some type of quantity, a quantity that changes over time, which means q could be thought of as a function. Q prime is the rate of change in that quantity. And this is an important thing, especially for the AP test. A lot of times they're going to have problems describing some kind of quantity, and they won't use symbols, they will just use words. And when they say rate of change in Q, you need to think that is Q prime. Okay, so by integrating the rate of change, meaning integrating the derivative, we will end up getting a net change. So this statement here is simply the fundamental theorem of calculus, but we call it the net change theorem. It says integrating the rate of change in a quantity equals the net change in the quantity. Another way this is sometimes phrased in the problems are they will give you the rate of change of something, and they will ask you for what is the total change. So total change should be a giveaway that you need to integrate. Right? That's really what when we say net change, you could also think of it as total change. Or sometimes they'll just say total amount. Okay, just as before, if you needed to get a future value formula, we could do the same trick we did before. Write this integration of an accumulation function. Fundamental theorem of calculus says that it's equal to this. The integral cancels the derivative. Plug in then those limits. If we add this to the other side, you get the formula for the future value of a given quantity. And again, just as before, it doesn't have to be 0. It can be any constant value there. Okay, so this next table just restates that exact same thing in both formulas. This also gives us a geometric way of thinking about net change. So the net change in some quantity over an interval AB is equivalent to the net area under the derivative. Not the net area under Q, but the net area under the derivative is the same as the net change in that amount. Okay, so let's try an example from biology. So suppose we have a culture of cells in a lab. It has a population of 100 cells at time t equals 0. And then suppose that the population increases at a rate given by this function. So notice it's increasing at a rate, meaning that this is the derivative of the actual population. Okay, so they say they want us to find n of t. So just as all the problems, you have two ways to do this. N of t is equal to n of 0 plus the accumulation function from 0 to t n prime t dt. Or we could just say it's the antiderivative of the rate of change plus some constant. And as with all of them, I personally just kind of prefer doing this. I feel like you're plugging in less when you do this, so all right, so we need to do the antiderivative of that. So this technically should be a u substitution problem. We should let u equal negative 0.1t, so then du would equal negative 0.1 dt. So we need to put that in the integrand, and we would also cancel it at the front. But I think this is one that we can kind of just do in our head. So we know that the derivative of an exponential function is basically itself multiplied by the derivative of the exponent. So in this case, when we're integrating, we're just going to divide by that. Right? This is really coming from when you do the u substitution, this has to be put out in front as a reciprocal. So hopefully we're okay with that. Okay, so this is really 1/10. If you do keep change flip, that's going to come up as make the coefficient negative 900. Oops. Oh, that's not good. Okay, so now we've got this, but we need to figure out the constant. And that's where we use the fact that n of 0 was 100. Okay, so if we do that, I don't know, I guess I'll do it up here. So n of 0, we plug 0 into that, is negative 900 e to the negative 0.1 times 0 plus c. Just plugging 0 into this. So exponent's going to be 0, so negative 900 e to the 0 plus c. Anything to the 0 is 1. But we know this is 100. Right? The initial amount was 100. Add the 900 over. So we have 1,000 is c. So then we can write our actual function. N of t is 1,000 minus 900 e to the negative 0.1 t. And I just flipped it around because it looks nicer. And I believe that's all they asked for on this one. All right, so this is just showing what we've actually done here. They gave us the rate of change. Notice that the rate of change is decreasing. If the rate of change is decreasing, but it's positive, that means the function should increase, because derivative is positive, should be increasing at a decreasing rate, which is actually what we see here. And the maximum population, the carrying capacity of this, actually turns out to be 1,000. If we took the limit on n of t, as t goes to infinity, this piece here goes to 0. So our population grows up to 1,000 and then stops. All right, I believe we just have one final example. This last example is kind of messy just because they made the table so big, but this is a really good example for what they will do on the AP test. They love the net change theorem. Guaranteed to see it on there at least once, and most likely it'll be in the free response part of the test. And this is really the style of how it's usually asked. Okay, so what we have here says the table below lists rate of change s prime of t and global sea level. Global sea level is just going to be s of t at various years. So 1995 is t equals 0, all the way up to 2011, which is t equals 16. So then they've listed rates for each of those years in millimeters per year. So if we go to 2002, at that time the rate of change in sea level rise was 2.21 millimeters per year. That's how quickly it was rising at that time. So we're going to make the assumption that the derivative is continuous on the closed interval 0 to 16, which is reasonable. It's most likely going to be a continuous function. We wouldn't expect rate of change to be able to jump instantaneously. And this says, explain how the definite integral can be used to find the net change. Well, I mean, there's not much to explain here. We know that net change, by definition, is s of 16 minus s of 0. And we know also that this can be written as the integral from 0 to 16 of s prime of t dt. This definite integral is equal to the net change in sea level rise. Now the problem is we don't actually have this formula. We don't know what the formula is for the rate of change in sea level rise. We just have a few points. But we can approximate this because we can graph these points out, and we could use a trapezoidal sum to actually approximate the area under this function. So that, I think, is what is next. All right, so we have that here. So this image shows, just plotted the y values for each of those points. So, you know, the idea would be there would be some nice curve that would go through all of them, but we don't actually know what it is. Doesn't matter, we're just going to approximate the area using trapezoids. So rather than have us write all of that out, I've already put it out here. So we can't use the shortcut rule because the width of these trapezoids are all different. So we have to use the generalized rule, meaning just find the area of every single individual trapezoid and add them up. So the heights, these heights you see here, are just directly taken from the table here. So that first s prime of 0 is just going to be the 0.51. This would be the 5.19. So you'd have to just put all those numbers in each of these trapezoids. The number you see here at the end on each one is the width of each trapezoid, and you can see it is changing. The first one has a width of 3, and a width of 2, 2, 1, 4. So each width is a little different. If you do all the math, according to our book, should come out to this value here. Notice that this is the net change in sea level rise. So the units are not a rate of change anymore. It should be the net change in S, meaning it is just how much rise actually occurred. So the total, in other words, the total amount of sea level rise. This is what I mean by in the problems that are typically just going to say what is the total of something. Well, the total sea level rise from 1995 to 2011 approximately would be 51.6 millimeters. Now you might just think that we should just be able to add these together, but that's not the case because the widths between them are not the same. So that's typically how this net change is applied. You're given rates of change, and then the question asks you for what is the total change in that quantity over a certain amount of time. And I believe that is the end. So hopefully you're still with me. Hopefully it wasn't too painful to listen to this, and good luck with the homework.